Good evening, everyone. I'm Silvio Ramos, fourth year mechatronics engineering student at São Carlos School of Engineering of University of São Paulo.
Good evening, everyone. I'm Henrique Crucial, fifth year mechatronics engineering student and a colleague of Silvio at São Carlos School of Engineering. Tonight, we begin the second and last international lecture of the 16th Sematron, brought to you by our sponsorship from Thor Labs. With us tonight, engineer Andres Moura, aerospace robotics PhD, and we'll talk about Astrobee, current status and future use as an international research platform. Now we pass on to Andres to introduce himself and begin the subject at hand. Thank you.
Hello, everyone. It's a pleasure to be here as part of Sematron. I'm really happy to be part of this event. Thank you very much to Sylvia for your organization and invitation to the event. I am really excited to be part of this. And hopefully for the next event, I will be able to meet you all in person over in Sao Paulo. Today, I would like to talk about my work here and the work of many others at the Astrobee facilities team, or here at Ames Research Center. So we are part of NASA, and we are one of the 10 centers that work for different research and towards space exploration. And in our particular case, we are looking towards automating and helping tasks that are really easy to do by human means to be automated by or carried out by robots, in this case, Astrobee. I will give you a little bit of an introduction of what Astrobee does, so just give me 1 second. Let's see if we can do this. And so, let's see if I can get this here. Yeah, okay. So, basically, Astrobee is not a robot by itself. Astrobee has the power of a research platform. This research platform involves several other components, namely the ground and flight units, the Astrobee research facilities, and the Astrobee robot software, as well as the access that we provide to the International Space Station. Another thing that we do is that, thank you for that. Another thing that we do is that we are providing people all over the world support so that we can take research from all these different venues up to space. And this research could be anything from artificial intelligence to manipulation to computer vision to human-robot interaction, and of course many other fields in the robotics and other fields that have nothing to do with robotics. And I hope that you will learn a little bit about this during my lecture. Here I just want to show you on the right side how we have a cycle, what I call the cycle, which is the let me just make my screen a little bit bigger. Yeah, there we go. There's a cycle where we have the guest scientists, or people that come to us to work with us, as the very first part and the top, as you can see here. Once we have that, the guest scientist starts learning how to program the robot using the Astrobee robot software. Then they develop their own their own guest scientist code, and then from there they move on to a test phase, which is using the simulator that we provide. By the way, this is already available for you guys right now over at GitHub. So just look at Astrobee over at GitHub. You will be able to download and start working just like we do here at Ames. Once you get that going, then you will be able to then move from the simulator to the hardware. And once you're in the hardware, you will then be able to move on to us, which is the facilities. Well, basically on the Astrobee hardware, you can already start playing with the hardware, but you will see the robot actually moving and doing things in our ground facilities. Once we have reached that point where everything looks like it's working fine, we go through the ops procedures and many other paperwork and other tons of work that had to happen. And then your payload goes to the International Space Station, where we run experiments, and those results are then returned to you. And that's how the cycle of this life goes. So if we go ahead and move here, we can see that the Astrobee started many, many years ago. Perhaps some of you guys were still very young when this started, but like for example, in 1996, the AER Cam Mini was the very first example of having a robot helping humans during space flight. This particular one was used briefly to help astronauts, or rather help mission control down in Johnson to understand what was the condition of the astronauts during their EVAs, or extravehicular activities. Then came PSA, which was completely developed, tested, and tested here at NASA Ames, where everything was working great, but it never got to fly. However, based on this effort, DARPA came up with a very good idea, and MIT came in with a very good idea, and DARPA supported it. And this came to be spheres, or the synchronized position hold engaged reorient experimental satellites. I hope that you guys remember what the Luke Skywalker back in the very first movies looked like, and how he was training with his laser, with his with his sword, and he was fighting against another robot that was circular and kind of shooting lasers at him, right? Blasters. So he was, this is kind of like a motivation for a professor to come up with an idea and a concept, and then spheres came up to be. After that, spheres has been extremely useful, and as a matter of fact, it became one of the most, if not the most, used platform, experimental platform inside of the International Space Station. And based off that, an extremely good success, the Ames Center started to work on Astrobee, its successor. And so Astrobee now has been already put in place, and we have started working with it as of 2019. Other free flyers exist, and those are the ones from our good friends at JAXA, and also at ESA or DLR. So the ones at JAXA is called InBol, and as a matter of fact, this one is going to be replaced by InBol 2. Then we have, that's a very small one. It's kind of like a 15 centimeter in diameter. And the other one is Simon. Perhaps you have heard of it. Simon was the very first AI-based, fan-propelled free flyer robot on board of the ISS, and he was working with one of the German astronauts in 2019. As I said, Astrobee is not only a robot, it's an actual platform, and this is a research platform. This research platform is comprised of at least 3 main components, which are the free flyer, the robot itself, the docking station, where the robot docks and communicates with the ground, with us and at Ames, and also it recharges and has a lot of other features. And then we have the ground data system, which is basically ground control for Astrobee. As you can see, Astrobee itself has been designed in a very modular fashion, so it's got its propulsion modules can be replaced easily, and then the core is being designed such that it can also accept multiple payloads. In this case, we have 1, 2, and 3 payload bays on board of every single robot, so that we can actually have a system going. One of the other things that we have here is that we have multiple computers inside of the robot, and we will see that in a second. Here we have a little bit of a better view of how the dock looks like, and the different sensors and other systems that we got. Here, as you can see, we have in the top aft, the top aft payload bay of the Astrobee, one of the first payloads that we got, which is in a sense an arm. It's a simple perching arm, as we call it, which is going to help the robot perch itself onto handrails, which are located all inside of the International Space Station. Then we have a series of sensors, the nav cam, side cam, the has cam, touch screen, which is essentially like having a cell phone or an Android cell phone on board. And then we have a series of interactive lights, LEDs, and also the screen itself, which shows eyes to demonstrate that the robot is alive and working. The dock station has a series of AR tags that allow the robot through its dock cam to understand where it is in the world and localize itself, and then allows it to dock automatically. Another thing is these berths allow the communication and charging, autonomous charging of the robot. Another thing is the robot software. Basically, we are heavily using the robot operating system. Perhaps some of you are aware of this and have used it before. And so this allows us to reuse. Basically, we are not going to reinvent the wheel. We are going to easily build on those capabilities, and then on top of that, allow for the community to come up and produce a different set of tools that may improve the quality of the robot. As I was saying, some of the features the software has is that it allows the robot to sense and actuate, sense its environment, actuate upon those sensing. It allows it to localize and navigate. It allows it to move around and also dock autonomously. We also can send commands to the robot so that the robot can be teleoperated. And it helps as well guest scientists, as I was saying earlier, to run their own code so that they can run experiments, either by only running what is called an APK or an Android package, basically an Android app, just like the ones that you have probably already developed before, and or through that same APK, command some hardware that is distinct to the guest scientist payload. And in this case, also another future work is going to be having multiple Astrobees working together and interacting with each other. The simulator in itself allows for the developer, or for, well, basically the guest scientist, to understand how the propulsion works, how the localization works, and how the models that we use for the imaging, the arms, and the lights work. Also, it's very useful because then allows a software in the loop simulation where the entire robot, the entire ecosystem can be run inside of a single computer. Then comes the ground facilities, as I was mentioning. Ground facilities are helping us to take into account, or to simulate rather, the same capabilities that we have on the ISS. In this case, as you can see here, this is the Granite Lab. And this Granite Laboratory is called like this because of its massive granite table that we have here. This granite table here, what it does is that minimizes the friction between itself and any surface or any other system that is put on top. And as you can see here, the robot itself is attached to a base, which in itself has two CO2 tanks, which push out the CO2 into valves that are basically making the robot levitate. In this way, by minimizing the friction and making it levitate, the robot is going to be able to perceive 3 degrees of freedom in microgravity simulated environment. that is going forward, left and right. So basically X and Y on translation, and then yaw-ing on the Z. So if we want to go further and now have up to 6 degrees of freedom, where we have both rotation on X, Y, and Z, and also translation on all those 3 axes, then what we want to use is the microgravity test facility, or MGTF. In this case, we are able to use a much larger area and volume and be able to generate maps and create different trajectories and test those trajectories and see if that is working as it is expected. So in terms of guest scientists, we have multiple guest scientists. As a matter of fact, we're full of experiments, and this is only our first year. All this summer, we spent a long time working really hard so that we could have the robot ready for what you will see later on is a competition here at the at the ISS. Using in collaboration with JAXA. So in this particular one, oh, and I'm sorry, I think I already missed one video that I wanted to show you, but let me just finish with this first. So this guest scientist program basically allows people from different institutions, even industry, to come over and work with us. So right now we have at least 6 different guest scientists, and those are Realm, that is basically a center. It's a group inside of Johnson Space Center. We have also MIT, JAXA, the Naval Postgraduate School, Stanford, and Astrobotic. From this, we have Astrobotic, Stanford, and JAXA already in, and I think Realm already inside of the ISS. And before I continue with this, let me just give you a quick example of what, or a better view of what Astrobee is. Let me just do that real quick. And so here is a short video, and I hope that you can see it and enjoy.
Flying more than 250 miles above Earth, the International Space Station is both a research lab and a stepping stone for future trips to the Moon and Mars. NASA is developing 3 Astrobee robots that will fly inside the space station alongside astronauts, opening research opportunities for guest scientists, and saving astronaut time by doing routine tasks. The Astrobees will replace the spheres, the current robots, and most used ISS payload. Fully autonomous, each 1-foot cube is packed with sensors that open up new areas of research. The Astrobees provide a zero-G research facility for guest scientists, give ground controllers additional eyes on the spacecraft, monitor radiation and air quality that help keep astronauts safe, and can even find lost items. The built-in arm normally occupies the top bay, but can also be swapped for a guest scientist's own experimental hardware. Like a quadcopter, Astrobees fly in air, except there is no gravity on the ISS. As a result, they are not limited by lifting power. Larger payloads can attach in a tractor-trailer configuration, and multiple Astrobees can even work together. 2 centrifugal impellers drive air through 12 adjustable nozzles that work together, allowing the robot to instantly move in any direction and turn on any axis. The Astrobees will continue the Sphere's tradition of hosting the annual Zero Robotics competition, drawing together thousands of students from 18 countries who can watch their code fly on the space station. Launching in 2018, Astrobee is the next-generation robot meant to make life in space easier for astronauts and, at the same time, build a foundation for new scientific breakthroughs in autonomy and robotics.
Okay, very good. So as I was saying, some of the steps that you have to carry out to become a guest scientist is that you have to first, well, contact our facility, and then you have to determine who, what, where, and how the guest scientist is going to carry out the research. Then the technical planning, development, and evaluations happen. And after this is when the operations phase, basically when the uh, guest scientist uses the hardware and the software developed the for the experimentation to happen on board of the ISS and the Granite Lab and all those steps. And finally is when you receive your experimental data. As I was saying, some of the interesting research that it is being carried right now are those of MIT, Johnson Space Center, Realm actually, which is basically creating or using the robot to move inside of the ISS, and while it's moving inside of the ISS, it's going to use an RFID tags that are attached to the different bags inside of the ISS, and by passing through, it will be able to communicate with those tags and understand how many of what is where. And with this, it will be able to create an inventory of the things that are inside of the ISS. And this task by itself is going to be able to help a lot of, to save a lot of time for the astronauts, especially because astronauts, the cost of an astronaut hour, I think, is in the order of thousands of dollars. So if you can really use that amount of that resource effectively, and not just go and simply tell the astronaut to go and fetch you a screwdriver or whatever, and you instead have a robot bring it back to you, then you'll be able to save that and be more efficient with the time that the astronauts are doing, so that they can actually do really more complex and difficult tasks, and specifically more experimentation, more science. And so JAXA, as a matter of fact, and I will talk about this later on, JAXA came up with our collaboration with us, in which they will they designed this competition, which is using Astrobee, so that students can create a set of algorithms that will run in Astrobee, so that it can solve a problem inside of the ISS. I'll show you a little video about this as well later on. Gecko, for example, or Stanford, is using Astrobee as a way to test a new mechanism that they have to attach to different surfaces, independent of what kind of surface or what kind of shape that surface has. So they're using the robot to come close and then attach to it, and then bring that object or wall, or even sustain the robot in one place. And Astrobotic is doing also very interesting work, which is basically using the robot movement inside of the ISS. And while that is happening, they're listening to all of the sounds and noises that are coming around the environment of the Astrobee. In this way, they will be able to map what is going on inside of the gem. And specifically, they will be looking for different events. For example, a leak. If there's a leak, or if there's a sound that it shouldn't be happening, they will be able to determine there's an issue, and then they will be able to alert the people that are next, or that are required to be alerted. Okay. So let's continue. Right, so as I was saying, MIT is one of the competitions that was used in spheres. And this competition basically, these are a couple of pictures made by interns at our facility, our lab. And what they're trying to show is how the students would have to write code to be able to shine light to these objects. Now, the trick here is that these objects are rotating and they have plants inside of them. So Astrobee has to go and take pictures of them while the rings are rotating. So this is just a, a proof of concept idea, but it actually hopes to show how things work. Now, the JAXA Kibo Programming Challenge, which I was mentioning, basically looked at how can they bring students together so that they can create a piece of software that can be uploaded onto the Astrobee, and then from a starting position, right, go onto another position and read an AR or a QR code in this case, and from that QR code, they will retrieve the coordinates, the XYZ coordinates of a target, or in this case, an augmented reality target. Once you get to the second position, this position will tell you the orientation that the robot needs to have once it reaches that target. And once it reaches the target, it will read the AR tag, and then it will let it know for how long it has to basically illuminate a laser so that it can go and try to aim at this target that you see here. So the one team that allows to that is able to shoot the laser and keep the laser pointed at that location closest to the bullseye, that's the one who wins. So basically, I wanted to show you how Chris Cassidy, one of the astronauts that worked with us, helped us immensely. So let me see if I can go back to that video. One second.
The unique thing about this particular one on the right docking station, it goes in upside down. Went and got some snacks, some nuts and some hot chocolate. So the scientific team is in California, the payload control center is in Huntsville, and of course I'm here. So we've got 3 different locations. We're all working together.
Subscribe for more space.
Right. So basically that shows you how it is that we work and interact with Astrobee, and basically how do we work with astronauts on board of the ISS. Now, let me just show you how this Kibo RPC, it's a very long video. I am not going to show it all. I'm just going to show you a little bit. But you can go and look it up here at jaxa.krpc.jp. So let's look at this video real quick. So this is a video from JAXA, and they talk about what the first Kibo programming challenge is.
Hi, everyone. Welcome to the first Kibo Robot Programming Challenge, the final round.
Okay, so I'm just going to show you, this is actually what happened this year, just a few weeks ago, over October 8th, I believe it was. And this is the view from the inside of the Japanese Experimental Module, or GEM. And you can see here where Honey, the other robot, is, and this right here is Bumble, the blue one. this little guy here is in ball, and this right here is the target I was talking about. And so this is the first, I think the first or second team. No, I think this is the second team that is trying to do, or that is doing the challenge, and it's the first time that they're really trying to do it. And we on the ground, we were very excited, very listening, paying a lot of attention. Now, remember, this is during the pandemic, so we were, like all of us, we've been working from our own places, our own home, and all of us are dispersed across the U.S. And our team is here in Ames, but even inside of Ames, we're inside of our places. And then there's people over in Johnson, people over in Marshall, and then of course the people over in JAXA, and then there are participants from Indonesia, participants from Australia, Thailand, Korea, and some other countries from the Asia Pacific region. And so this is the moment when the first, I think Indonesia was coming in. And so listen to the exchange that is going on. It's just a minute or two. Oh, 1 second. One last thing is that the robot is being moved by the code that the students wrote. And so this is the first time that any student ever is done this on board of the ISS and on board, it's not on board of the ISS, but on board of the Astrobee inside of the ISS.
Oh. Oh, the target is
here you can see the video coming from straight from one of the cameras from Astrobee. And here's Chris Cassidy just floating around.
Wow, Indonesia got a tough run going here.
That's Chris.
So this is the camera of the Astrobee.
And here the robot is about to be in position.
Laser illuminated.
Wow.
And you can see there the light, the laser being illuminated and shooting
to the
it.
target. Really close.
This is fabulous, Chris. I wish you could hear the engineering team down here. They're pretty excited to see this happen. This is really amazing.
Yeah, great.
That was impressive, I gotta say.
Oh, great.
I hope you realize that you're playing a big part in this. All these weeks of rescuing.
These are the actual students being online, looking at the work.
Culminating right now. This is happening.
It was really exciting. Okay. So after that, I just wanted to tell you that there's, of course, the near-term guest science payloads and the NASA, as I was saying, RFID Recon. Then there's MIT, there's the Stanford, and JAXA and Astrobatics. So, you know, who knows, in the future, perhaps there's going to be students from Sao Paulo, Sao Carlos, and going to send their payloads to the ISS. So some future applications that we have here are those of the having multiple robots being part of multiple robots that are going to be part of the future of exploration, and specifically for architectures that are required to be the foundation towards completely autonomous systems. And with this, I mean systems that in the future, when we have space stations such as Gateway that are going to be in the way, in the middle between the Earth and the Moon, they are not going to be able to be maintained by humans all the time. They will require robots to have deliver this maintenance and do it very properly and in a constant fashion. So by allowing this monitoring and this maintenance, we are right now learning what are the biggest issues that we have inside of the space station. What are the biggest issues that we have with robotics? What are the issues that we have to address between the so that we can get a collaborative capability between humans and robots in space, and also that they can take care of a number of functions like checking for leaks or doing automated surveys or having localization problems and things of that sort, as well as when there's a new shipment coming in into the station, maybe the robots can by themselves take it into the station and then stow it properly. And I think with that, I would like to finish my presentation and have a good amount of questions if you want. If you have any questions, of course.
We probably have a question.
Mm-hmm.
So, Diogo asks us, do you think that these researchers made with Astrobee could be implemented in other areas other than the ones common to it? For example, a robot that could help people with physical disabilities.
There is, yes, of course, yes. There is certainly a lot of different aspects that can be used in which the robot can be used. Certainly, one of the biggest limitations to transfer from microgravity environment and Earth is, well, gravity, right? So the aside from the locomotion mechanism, I think that there are a lot of parallels between what we are doing right now and what can be done to take care, for example, of the elderly. The one thing that we want to demonstrate here is that the robots will be able to have minimal supervision both from the ground and from the station. And with this capability, we are trying to demonstrate that the robots themselves are able to work on a more collaborative rather than a supervisory role. Mm-hmm. So that's a really good question, yes.
And we have another one. Gabriel asks, is there any possibility of making an Astrobee that can work on vacuum and be used outside the spaceship?
That's a great question, yes. So let me just go back here. That's a really good question. So thanks for that, Gabriel. As you can see here, these are our propulsion modules. We made Astrobee in a way that they can be detached and then they can be attached again. The reason for that is so that different researchers can do different things with the robot. One of the things that are being done right now is that of Realm RFID, where Realm actually places an RFID antenna here that is connected to their own payload attached to one of the payload bays inside of the robot. So that's one of the physical modifications that you do into these propulsion modules. Now, can we take the robot as it is right now to outside? Of course not, because the robot, what it does is that it sucks in air through this impeller and keeps a pressurized environment here. And then in order to move, it opens and closes all these nozzles out here so that it will, if it opens the ones on the top, it will go down. If it opens the ones on the back, it will go forward. So what you have to do is to come up with a way to basically create a propulsion module that is not dependent on air, perhaps CO2 or any other form of propulsion, which in itself is already a research that anyone could do. You could do it, and then create those modules, attach it to the robot, protect the robot accordingly, because of course you will not be protected by the different layers of the ISS. Now you're going to be completely exposed to the radiation that it's out there in space, several different types of radiation. And so with that, you will have to also protect the core. But other than that, you would be able to snap in another propulsion module and then go out and do your work. So yes, it's totally possible.
We have another question, Cody. He asks, does any thought have to go into making the Astrobee safe in their interactions with humans? For example, to avoid collisions between them?
Oh man, Cody, that's a fantastic question. You have no idea how much pain we have to go through in order to design the robot properly. I hope that you are able to see this, but here, do you see these bumps, these bumpers, maybe? You see this picture here? You see how in the corners it has little bumpers? Can you see that? Yes? Maybe? Okay, so hopefully you can see it, but all of this here, we have to go, well, not personally, but like the team had to go through a very, very, very lengthy set of requirements that are in place such that they will absolutely determine that the robot is safe for itself and also for the interaction with humans. And so, as you can imagine, all of these requirements go down or trickle down into different areas of the design of the robot, from propulsion to electrical to mechanical to software. All of it has to be able to work properly, but also be able to not be a hazard to itself, to the space station, and also to the human. For instance, we have to being able to demonstrate that certain LEDs, for example, the ones that we have on the side. Let's see if I can go here somewhere where we have a bigger. So, for example, these LEDs right here, these are LEDs. Its intention is to serve as a human-robot interaction system. And so if the LEDs change color or if they are only certain LEDs turn on, they should have a certain meaning. But the point with these LEDs is that they have to go through a analysis of how bright they were, where they were, and how hot they get, how much current they get, and how often do they get turned on. All of that is put into the design of the robot so that we can put the robot up in space and be able to qualify to have an interaction with the astronaut. So yes, it's a very lengthy, very developed, very complex process. And yes, every single thing that you see in the robot has been thought so that it can be safe to interact with humans and also among themselves and the ISS.
And could ask, I've heard recently about soft robots and that they are good for human and robot interactions. Are there any soft robot design concept implemented in the Astrobee?
There are right now. There's only, let's see. There are two ideas that are going to be implemented. That's a really good question, Cody. So there are two ideas that are going to be implemented. Research from guest scientists. And so those ideas are basically tackling the same issue through different solutions. One is Gecko, and the other one is called Reggae. Why Reggae? I don't know, but that's how they call it. So the one from Gecko, basically what they have is a system that by exerting certain changes in the shape of a plate, it can attach itself to different surfaces. For example, it can attach to this cup and then move it around. So it's not necessarily like soft robotics, but it's close enough to that. And then there's another one, which is Reggae, which has a similar idea. But what they're going to be doing is testing different materials, all of them soft, that are aimed to check how easy or hard it is for them to sustain after being in contact, after a collision, to sustain that collision and then be able to move together. So that's a very those are two aspects of robots or of robotics, and specifically soft robotics, that are happening right now. But there's going to be a lot, I can assure you. And of course, if you have the ways to run research with us, then we'll be more than happy to help you with that too.
Next question is from Douglas. Is it possible that, in the future, robots can substitute astronauts in space?
That's a tricky question. I don't think that robots right now or in the near future, not even in the mid future, will be able to substitute humans for everything that humans can do. I don't think that that will ever happen, but I think that for certain tasks, it is something that they can do. And it's an easy example. Look at right now. Look at Tesla, for instance, or look at other, um, companies that are working in the automation of driving. All of those companies are using software to implement it inside of a car so that the car can drive itself. That is not necessarily replacing humans, but is helping humans to do certain things better and more efficiently. So it's not that they're going to replace them, but they're going to perform certain tasks that humans can do, but not necessarily are interested in doing, right? So in this case, Astrobee is trying to learn and set the foundations for what we can do in the future. Learn what mistakes we're making, and so make better robots in the future that will be able to do maintenance inside of future space stations, and to collaborate effectively with humans, so that the system becomes more independent from humans, and then they can do their own tasks. But I don't think that robots will be able to completely and for every single task replace humans. I don't think so.
And the next one, Gabriel asks, do you think that in future we will be able to use Astrobees in Earth despite gravity?
Well, I think that there are a lot of different solutions that we can use inside or in the presence of gravity. Astrobee certainly has a number of very interesting approaches to what it does: navigation, localization, interaction with humans. But certainly there you will have to go through a substantial number of changes into its software and hardware so that it can work inside of the inside of an environment that has gravity. Now you could say that Astrobee could work as a 6 degrees of freedom robot, just like a quadcopter. So why not?
Then Fabio asks, do we have any research about transforming solar power into propulsion by propelling electrons that will allow recharging sites in orbit, creating rich waypoints for robots to travel from stations?
Do we have, let me see if I can understand this one. Oh, I see. Okay, using solar power to translate that power into a propulsion. I'm sure there's got to be some, but I am not familiar with that field of research, so I wouldn't be the best person to answer that. Mm-hmm.
While we get another question, do you have any? We don't have any more questions in the chat.
Oh, sure. I'm more than happy to hear any other questions that students or comments.
Comments on the solar power on in orbit? Or you don't really?
Well, right now systems basically solar power is of incredibly high importance. Of course, it's one of the sources of power that we get. I know that there's a lot of development right now in terms of electric propulsion using a small, very small to the level of CubeSat, small propulsion systems. I have a really good friend that has been working on that as his PhD dissertation, where he uses sort of plasma to transform a gas into a propulsion, into a system that can be propelled through electric propulsion. So I think that that's a very interesting field of research. It's not my field of research, so I cannot really talk about that, but I think it's very promising and very interesting.
So we have questions from Thales about Astrobee simulator on GitHub. Can it be used for more general simulations? For example, drum simulations with a certain scenario.
Sure. So as a matter of fact, ROS, because remember, we are using ROS. So this is the robotic operating system. The robotic operating system uses a series of dynamic engines. And one of them is the gazebo. Gazebo is also a visualizer that allows for these models to be represented in the real world. And so based on that, you can have simulations using all sorts of different kinds of robots. They can be crawling robots, they can be underwater robots, they can be flying robots, they can be, as you can see, space robots. So yes, it can be used. Now our system directly, I don't think can be used for drones. I think it will be, although I think it is possible, I think it would be easier to just use the regular ROS system to work on directly the model of drone or quadcopter or hexacopter, whichever configuration of UAV you're interested in, and then create the scenario that you're interested in.
Cody asks, with the Astrobees in action, what do the astronauts do with their extra time?
Ooh, a lot of things. So they wake up usually at 6:30 in the morning, and they don't stop until like 6 p.m. at night. So with that time, they are out of that time they also work out every day 2 hours. So the work that Astrobee is looking for, or the work that Astrobee is looking to do here is to collaborate with humans, in this case astronauts. And so what they're doing is, for example, if the robot is doing some surveying, or doing some inventory, the human, in this case the crew member or the astronaut, basically will not have to do that. So in this case, the robot will be doing a check on what is going on the robot, right? Or I'm sorry, on the robot, not on the inside of the ISS. And so while that is happening, the human can do its science, its work, and can collaborate with a number of other people down on the ground. So imagine it this way. Imagine that in the morning, that every single day you have to, clean your house. So you have to, use your broom and then scoop the dirt and then put it out. And then you have to, use some other tool and then clean the floor and then do the dishes and all that. So imagine that all of those things are things that you have to do anyway, so that your house is clean and you can actually, do some work. So in this case, there are Roombas right now, or robots of that kind of sort, that are now vacuum cleaners. And so you can program those vacuum cleaners to do their work, at any time. And so with that, you won't have to worry about, cleaning the floors or doing the dishes. Now you can focus on really working and having a more time. And if you are more free, then hey, that's great. So that's kind of like what Astrobee is aiming to.
So, and Isabella asks, in case the Astrobee breaks, can you repair in a remote way or in the space station?
What a wonderful question, Isabella. Thank you. As a matter of fact, I was part of the Astrobee facilities team that worked on our first payload, and our internal payload. It's called port tester. And that port tester payload is kind of like an stethoscope. And the stethoscope is that little thing that doctors, physicians use to listen to your heart, right? Like breathe in, and then they listen to you, right? So port tester is a little box that is connects to the robot. And thanks to that little box, astronauts inside of the ISS will be able to tell us if there is something wrong with the robot. If we can do that, and we can check if there's something wrong with the robot, we can then from here, from the ground, try to fix the issue in combination and in collaboration with the astronauts if that was necessary. If that tool, if that payload didn't exist, we would have to send the robot all the way back down, and then after that send it back up, and basically, to service the robot and make sure that it works fine. And that is very costly. It's very expensive, as you can imagine. And so by doing this, we're saving thousands of dollars, and people will be much, much happier, and of course will be much more efficient.
João asks, are there any limitation in Astrobee in terms of withstanding space radiation?
That's a really good question, Joe. So the problem with the space radiation is that it's everywhere, right? It comes from our sun, and there are many other types of radiation all over the spectrum. So the good news for us and for our scope is that we're inside of the ISS. We only work inside of the ISS. And because we're only inside of the ISS is that we are protected by the mechanisms that are already in place inside of the ISS. So just like humans can just be inside with a shirt or with a jacket, the robots can work just like that. So we don't need any special thing. Now, if we wanted to go outside of the ISS, we will definitely require a different set of protection against all different kinds of space radiation.
So we have the last questions from Douglas Martins. What do you think of the future of space exploration?
What do I think? I think it's very promising. I think it's very exciting. I think we have a lot of very bright people all around the world that are going to and are already doing a lot of work to make exploration easier, better, and more complex, closer and closer to what we can do as humans, and helping humans to get out there. So I think that we're going to do a lot of very interesting research, and a lot of people all over the world are doing that. I think space exploration also unites people from all different backgrounds, from whatever different religions and from different nationalities. And I think that that is very useful and good, so that we can all, go towards a better future. So I'm very excited about the future in space exploration and what it means for us as a species.
On behalf of Patron Group, I would like to thank Tor Labs for sponsoring us, as well thank Antônio Ueta, PhD professor, Instituto Nacional de Pesquisas Espaciais, for helping us contact Andrés.
Thank you, Andres, for the talk. You now have a moment for your final regards.
I am really happy to be part of the Sematron, the 16th time that you guys are doing this. I'm very pleased to have been part of that at this event. And as I said, I'm very much looking forward for the next time when we can talk, hopefully in person, and hopefully visiting you guys and have a more interactive talk with you guys.
We would like to remind the viewers of the Feira de Pesquisa e Projeto. It will start at 9 a.m. Brazilian time tomorrow. Good night.
Good night.
Good night.